This video provides a brief guide to B-trees, describing what they are and how they are implemented. B-trees are self-balancing search trees supporting fast search, insertion, and deletion operations that are widely used for databases and file systems. They were introduced in a seminal 1970 paper by Rudolf Bayer and Ed McCreight while working at Boeing Company. At this point, a question may already have risen to the forefront of your mind. What does the B in B-trees stand for? Could it be balanced, bushy, or perhaps Boeing? Somewhat enigmatically, co-inventor Rudolf Bayer simply says that the more you think about what the B could mean, the more you learn about B-trees. So we'll leave it at that. From the perspective of complexity, the self-balancing nature of B-trees means that their worst-case runtime for search, insert, and deletion is big O of log n. The storage costs of B-trees grow linearly with the number of stored data items. B-trees are balanced search trees, where nodes in the tree can have many children, for example, thousands of children, rather than the pair of children seen in various binary search tree data structures. Here's an example B-tree, where each node can have at most 4 children. You'll see that throughout the tree, each key in the parent node, such as the 4 here, subdivides the key ranges in its corresponding children. Here, 1, 2, 3 from 5 and 6. Similarly, 19 separates 17 and 18 from 20 and 21. The higher branching factor of B-trees relative to binary search trees leads to reduced tree height. For use case involving storage where nodes are stored on disk, this has the critical benefit of causing fewer disk accesses. B-trees and their variants have many applications that relate to storage. Examples include usage in MySQL, the Apple file system, and the B-tree file system used in some Linux systems. Before going into B-trees in detail, we'll take a short digression to talk about memory. Computer memory is typically arranged in a hierarchy. Within the CPU, we have small and fast registers. Next, we have slower but larger cache memory. Then, we have slower but larger main memory, or RAM. And finally, we have very large and very slow external memory, typically formed of hard disk drives or solid-state drives. As we move up the hierarchy, storage gets faster, while as we move down the hierarchy, storage gets larger. While it's always good to keep this hierarchy in mind, for many problems of interest, we really care about 2 levels in the hierarchy. The first is the level that can store all the data items that are relevant to solving the problem we are currently focused on. And the second is the smaller and faster level directly above this level. We care about levels because at each point in the hierarchy, the level above can be orders of magnitude faster than the level below. And so transferring data across adjacent levels is often the bottleneck in program execution. For instance, if we can only fit our problem into main memory, we focus both on this level and how data moves in and out of cache. If we can only fit our problem into external memory, we focus both on this level and how data moves in and out of main memory. One thing that makes B-trees popular is that they are well suited to working efficiently with memory hierarchies. While we could focus on any pair of levels, we'll focus on the pairing of external memory and main memory, which is often the context in which B-trees are used, but they are still applicable for cases when the higher level is the cache and the lower level is main memory. One widely used form of external memory is the hard disk drive, a technology introduced in 1956 at IBM. Here's a simplified picture of a hard disk drive. We have platters coated in a thin magnetic layer that rotate around a spindle. We also have access arms with actuators that are responsible for positioning electromagnetic read-write heads extremely close to the surface of the platters. The thin circular region of platter traced out under a given head position is known as a track. And since all arms move together, it is associated with a set of corresponding circles on each platter, collectively referred to as a cylinder. The platters for current disk drives typically rotate somewhere between 5,000 and 15,000 RPM. Now, the arm movements are a miracle of modern engineering in terms of their speed, but they are still slow in relative terms, so seeking to a particular piece of data on disk is slow. For this reason, data is typically stored in blocks that occupy contiguous regions of tracks. Once the read-write head is in place, it stays stationary while the platter spins beneath it, and consequently, reading and writing neighbours within a given block is relatively fast. SSDs, which form a growing share of the market, have lower latency than hard disk drives, but still a higher latency than main memory. This is true for both SATA SSDs and the increasingly popular NVMe SSDs that increase throughput by using PCIe sockets. Similarly to hard disk drives, SSDs also use blocks for data access. So accessing multiple neighbors within a block is much faster than accessing multiple neighbors across different blocks. A key idea behind the usefulness of B-trees is that we can make the number of children as large as possible while ensuring that each node fits in a single block. Then the process of navigating down a shallow but wide B-tree involves very few disk accesses. For example, suppose that we can have 200 children, or equivalently 199 keys, at each internal node in a B-tree, with the same number of keys at each leaf node. Then, a B-tree with a depth of 3, where every node is full, will contain 1 plus 200 plus 200 squared plus 200 cubed nodes, which is 8,040,201 nodes. Assuming we always keep the root node in memory, this means that we can access any of roughly 1.6 billion keys using at most 3 disk accesses. Remarkable. When performing our accounting for the speed of B-tree operation, we've seen that reading and writing blocks from disk is expensive, so it's useful to keep track of both CPU operations and the number of times we read or write a block from disk. Each time we want to access an object U that is not in memory, we need to read the block that contains it, which we'll do with a readBlock function. When we want to store changes that we've made to U, we'll need to write its block back to disk, which we'll do with a WriteBlock function. We now come to the B-tree definition itself. Before we define it, I'll offer you a warning. There are many different notation and definition conventions for B-trees. For example, those of Bayat and McCreight in their original paper, Knuth in his The Art of Computer Programming, and CLRS all differ in terminology. We'll base our definition coarsely on that of CLRS. A tree is said to be a B-tree with minimum degree T if, first, each node U has the following attributes: a collection of keys stored in a list in ascending order, and a Boolean value of whether U is a leaf node. Second, each internal node U has a set of children. This we also store in a list, whose length is 1 greater than the number of keys. Third, the keys of a node U bound its children's keys in the sense that each key, written key j of U's ith child, lies between U's ith key and U's i+1th key for any valid value of j. Fourth, all leaves in the B-tree have the same depth. Fifth, all nodes except the root have at least t-1 keys, so that internal nodes have at least t children, and that is why t is called the minimum degree. And lastly, all nodes have at most 2t-1 keys, so internal nodes can have at most 2t children. One particular case is sufficiently well known as to have a special name. When t equals 2, the B-tree is known as a 2-4 tree or a 2-3-4 tree, because each internal node can have between 2 and 4 children. One immediate consequence of this definition is that the height of a B-tree grows as big theta of log n. Here, we'll focus on showing just that the maximum height of the tree is bounded by a logarithmic function. The number of nodes in a tree of maximum possible height is obtained by having the minimum number of children at each depth, i.e., one node at the root with 2 children, that each have t children, that each have t children, and so forth. We can compute the sum of this geometric progression as follows. The number of keys is t-1 in each node except the root, which gives us this expression. The t-1 terms cancel to give us 2 to the h-1. We can rearrange this and take logs with base t to find that the maximum height of the tree, which we'll write hmax, is the floor of log base t of n+1 over 2. The floor operator comes from the fact that we are now considering the maximum height for any tree, letting n range freely, rather than restricting ourselves to the maximally tall and skinny B-tree that is only possible at certain values of n. One point to note here is the base t in the log. Since t is typically much larger than 2, this means that B-trees are usually much shorter than binary trees. Lastly, there is a nuance here about notation. Since t is a hyperparameter of the tree that is fixed, we can still use big theta of log n, rather than big theta of log base tn to describe asymptotic complexity, since the change of logarithm base amounts to a constant factor, which you can see by examining the change of logarithm base formula. However, Some authors like to conduct fine-grained analysis of B-trees as a function of both the minimum degree t and the number of keys, in which case we need to keep the base t in the logarithm. You may encounter both notations. We'll use the second. We now come to search, which we'll implement in Python with a recursive search procedure. The arguments to the search function, in addition to an instance of the B-tree itself, are a node u representing the subtree in which we want to search, and the key we are searching for. Since the keys at each node are ordered, we first perform a simple linear scan to find the lowest index where u's key remains at least as large as the query key by creating an index variable I and iterating it through the position of the keys until the query key is bigger than one of the node's keys, or we run out of keys to compare to. If we have found the key, we return the current node and the key position. Else, if u was a leaf, our search concludes unsuccessfully. Otherwise, we perform a block read to fetch the ith child of u into memory, and call the search function again recursively on the child. Let's see how this works on an example B-tree, in this case an instance of a 234 tree, where we'll suppose the arguments are the root node and the query key 11. Entering the function, we first proceed to the linear scan while loop, which immediately exits since 11 is smaller than 13. We do not have a key match and u is not the leaf, so we fall through to performing a block read to pull u's 0th child into memory, and recurse using this child and key 11. We then perform another linear scan until we've moved past all keys, since all these keys are smaller than 11. We check for a match, check we're not at a leaf, read the block holding the ith child into memory, and recurse further down the tree to this child. This time, we break straight out of the while loop, since 11 is not greater than 11, hit our matching key statement, and return the current node and the value of the index I, which is 0. Since the keys are in order, you may observe that we could replace the linear scan with binary search, which is logarithmic rather than linear complexity. However, it is not always beneficial to do so, since linear scans can be more cache-friendly. The current Linux implementation of a B-tree variant, for example, uses linear scans rather than binary search. When it comes to complexity, we follow CLRS and consider how costs change as a function of both the minimum degree t and the number of keys n. We saw earlier that the height of a B-tree with minimum degree t is big O of log base t n for n keys. The CPU cost of search involves a linear scan costing big O of t at each node, leading to a total cost of big O of t log base t n. If binary search is used, this can be dropped to big O log t log base t n, or equivalently log n. We perform one disk block read at each level of the tree, so there are big O log base t n disk accesses. We now come to B-tree insertion, which is where things start to get a little spicy. The basic idea is simple enough. We search for the appropriate leaf node and insert the key. But what if that node is already full? Then we will split the full node into two separate nodes at its median key. The keys to the left of the median key go to the first new node, and the keys to the right of the median key go to the second new node. Then we move the median key up into the parent of the node we just split. But what if that parent is already full? You can probably see that some kind of recursion may be needed. Broadly speaking, there are two strategies for performing B-tree insertion. The first, which I'll call insert then fix, is the strategy used in the original B-tree proposal of Bayer and McCreight. Here a key is inserted at the appropriate leaf, then we reverse back up the tree, fixing issues by splitting nodes where needed. The second, which I'll call the fix then insert strategy, is the algorithm described by CLRS. Here we split any full nodes that we encounter on the way down from the root to the leaf, then insert at the leaf. This elegant second approach has the benefit of being a one-pass strategy, in the sense that we only go down the tree, we don't need to go back up. Fix then insert is the approach we'll adopt here. Here is the insert function, which takes in an instance of a B-tree and a key to be inserted. We first create a variable to point to the tree root. Then, if the root is full, which is to say that it has 2t-1 keys, then we call a helper function called splitRoot, which creates a new node that is set to be the new root. It takes one of the original root node's keys as its key and generates two new children. Now we are confident that the root is not full. We call the insertNotFull helper function to insert the key into the root node. One important point to note here is that this call to splitRoot, which we'll see implemented shortly, is the only way that B-tree height increases. Before providing Python code for the helper functions we've just described, We'll first describe one other helper function called splitChild. This splits the ith child of a given node U, where the child is assumed to be full and node U is assumed to be not full. Our function takes as arguments an instance of a B tree, the node U, and the index I of the child to be split. We first create a variable to hold t, the minimum degree of the B tree, as a convenience. We then create a second variable called fullNode to point to the full ith child of U. Next, we create a new empty node and set its leaf status to match that of the full node. We give the new node the set of keys larger than the median key from the full node, and if the full node was not a leaf, we also give the new node its corresponding children too. Then we insert the new node as the I+1th child of U, and insert the median key of the full node into position I. All that remains is to update the full node so that it holds only the lower t-1 ranked keys of the keys it held previously, and the corresponding t children. Last, we perform block writes for the full node, the new node, and U, so that their updated state is stored on disk. To make this a bit more concrete, let's see this function in action on an example B tree where the minimum degree is 3. We'll first duplicate the tree to help us keep track of things visually. U is the top node, and we want to split its middle child corresponding to I = 1. We first assign t the value of 3, assign full node to the ith child of U, and create a new node whose isLeaf attribute we set to false, since full node is not a leaf. Next, we copy the keys to the right of full node's median key over to new node. Since it is not a leaf, we also copy the corresponding children over. Next, we insert the new node as a child into U in position I+1, and insert the median key of full node, which is 7, into the ith position. We then keep only the keys to the left of the median in the full node, as well as only their corresponding children. Finally, we write the blocks containing the full node, new node, and U back to disk. One last point to note here, our Python code aims to be clear, but it is not optimized for efficiency. We are now in a position to implement the splitRoot helper function, which splits the root node when it is full. It takes an instance of a B tree as an argument. The function first creates a new root node and sets its isLeaf attribute to false. Next, it sets the children of the new root to be a list containing the old root and updates the root of the tree to point to the newly created node. The function then calls the splitChild helper function we introduced earlier, and finally returns the new root. Let's see how this function operates on an example, this time a full root node for a B tree with minimum degree 3. As before, we will duplicate for clarity. Our first step creates a new node, then sets its isLeaf attribute to false. We then make the old root the child of the new node and update the root attribute of the tree. Finally, we call our splitChild helper function and return the root. Note that the tree height has increased by 1. As we noted earlier, this is the only way that the B tree grows in height. The last helper function we need to fill out our implementation is insert_not_full. As you might infer from the name, this function is going to insert a key into a node that is not full, recursively descending the tree and ensuring that any node it descends into is not full. The function takes as input an instance of a B tree, a node U representing the not full root of the subtree for insertion, and a key to insert. The function first initializes a counter, then iterates over U's keys via a linear scan to find the position where the new key should go. If U is a leaf, then the new key is inserted, shifting the existing keys over, and the block containing U is written to disk. If U is not a leaf, we read the child corresponding to the key position into memory. If this child is full, we split it with our splitChild function to ensure that we never recurse into a full child. We then determine if we want to insert into the left node or right node resulting from splitChild, and recursively call insert_not_full on this node. One point to note about this function is that it is tail recursive, so we only need to keep at most a constant number of blocks in memory. Let's walk through this function with an example B tree with a minimum degree of 2, calling it with the root and a key of 10 as arguments. As before, we first duplicate the tree for clarity. Starting at the root node, we first perform our linear scan to find the position of the query key, and since 10 is bigger than 4, I is incremented to 1 before the while loop exits. We then check if the current node is a leaf, which it isn't, so we go to the else statement. Next, we read the block containing the ith child of the current node into memory, and check if that node is full. It isn't, so we call insert not full on the ith child of u. We do another linear scan, incrementing I from 0 to 1, since 10 is bigger than 6. Again, we check if u is a leaf node, which it isn't. So we go to the else statement and read its ith child into memory. We check if the ith child is full, and this time find that it is. So we call split child to make room for the new key, which pulls the median key of the child up into u in the process. Next, since 10 is larger than 8, we increment I by 1, and can now safely call insert not full again. We do another pass through our linear scan, incrementing I to 1, since 10 is bigger than 9. Then we perform our leaf check, which this time evaluates to true, and simply insert 10 at the ith slot as required. Finally, we write the block containing u to disk, and we are done. The complexity of the overall insert function in CPU time is big O t log base t n, since we do one pass down the tree and perform at most linear complexity operations at each level. In terms of block reads and writes from disk, we do a constant number at each level of the tree, so that the overall complexity is big O log base t n. The final operation we look at is B-tree deletion. As with red-black tree deletion, this is quite complicated, so hold on to your hats. We'll break it down into steps. In a similar style to insertion, our idea is going to be to search for the relevant node and delete the key. This time, rather than the node becoming too big, we need to worry about the node becoming too small. With a similar mindset to insertion, we'll use a fix then delete strategy, where we only recursively call delete on a node that has at least t keys, so we know it's safe to delete one key without violating the B-tree properties. It's another one-pass strategy that means we'll only do one pass down the tree. This is just like when in insertion, we ensured that a node was not full before we recursed into it. To achieve this strategy, we may need to transfer a key down from the current node into a child before calling delete, since the B-tree definition only guarantees t-1 keys in each node. Still, that's okay, since in our recursion we'll ensure that the current node has t keys. There are 3 logical deletion cases for us to handle, which include when the search reaches a leaf node, when it reaches an internal node containing the target key, and when it reaches an internal node without the target key. We'll now look at the first few lines of a delete function, which we'll break down into parts because it's quite long. This takes in an instance of a B-tree, a node u that forms the root of the deletion search, and the key to be deleted. The assumption here is that u either has at least t keys or is the root. Our first step, as with previous functions, is to perform a linear scan to find the position of the key to be deleted amongst the current node's keys. Once we've computed this position, we are ready to handle the various cases that can arise. One extra point to note here: if, after handling the various cases, the root ends up with no keys, then it is deleted. Its only child then becomes the new root of the tree. When this happens, the height of the B-tree is decreased by 1. Let's look first at case 1, where the search reaches a leaf node. Continuing our delete function from before, we'll consider the case when u is a leaf. The logic is simple. If we find the target key amongst u's keys, we delete it, and write the block containing u to memory. Otherwise, we raise a key error to indicate the key was not found in the tree. Either way, we then return. Note that we are confident that it is safe to delete a key without violating the B-tree properties, since we always assume that u has at least t keys when delete is called on it. Next, case 2, which occurs when the deletion search reaches an internal node that contains the key we are planning to delete. This case has 3 subcases that we must handle, which depend on the number of keys in u's ith child and u's i+1th child. Our code continues from before, and first confirms that we are indeed in a case 2 scenario. In case 2a, we assume that the ith child of u has at least t keys. In this scenario, we find the predecessor key of the one to be deleted in the subtree rooted at the ith child. Then we delete this predecessor from the subtree and use it to replace the target key we want to delete. In case 2b, we handle a symmetric scenario, where instead u's i+1th child has at least t keys. Here we find the successor key in this subtree, delete it from the subtree, and use it to replace the key we want to delete. Finally, in case 2c, both child I and child i+1 have only t-1 keys. Here, we merge them together using a helper function we'll see shortly. Since the merge involves pushing a key down from u, we check in case we've made the root node empty. If we have, Then we update the root to point to its only child, which has the effect of decreasing the tree height by 1. Finally, we call delete on the child, now confident in the knowledge that it has at least t keys and won't produce a violation. One extra point. You may note that we've omitted calls to read and write blocks in this function snippet, a convention that we'll also follow for the remaining cases and helper functions to prevent the code getting too long. However, they are not complicated to add back in, and you can find code that includes them linked in the video description. Let's first look at an example B tree when case 2a has arisen, which we'll duplicate for clarity. Here, we call delete with key 9 on the top node. The linear scan in the preceding code has moved us into position with I equals 1, so that our conditional evaluates to true. The ith child has t keys, so we search for the predecessor of 9 in this child, which is 8. Then we recursively call delete on the ith child to remove the predecessor and use it to replace the target key, completing the deletion of key 9. Since case 2b is symmetric, we'll jump on to case 2c. Suppose we have the following tree, which we duplicate for clarity, and suppose we are deleting key 2 from the top node. Since this has position 0, and both of its immediate children only have t-1 keys, we call merge children, which has the effect of combining the children and concatenating their keys on either side of the target key 2, which is used to form the median key. We then check if we've made the root empty, which we haven't here, so we then proceed onwards with a further recursive call to delete on the combined child. Onwards to case 3. Here, we consider the setting when search reaches an internal node that does not contain the key to be deleted. The strategy for case 3 is to keep searching down the tree while ensuring that the next node visited has at least t keys. If it does not initially have at least t keys, we apply either case 3a, in which at least one of the node siblings has at least t keys, or case 3b, in which neither sibling does, and we need to perform a merge operation. Continuing our delete function and coming to the case when u is an internal node and does not contain the target key, we first check if the node that we will descend into next in our search has at least t keys. If it does, we simply call delete on this node and continue our recursion. If not, then we first handle case 3a, in which at least one of the ith child's siblings has at least t keys. We use a simple helper function to work out which sibling has at least t keys, and assign the index to j. Suppose it was the sibling to the right, so j takes the value I plus 1. Then we take the ith key from the current node and give it to the ith child, and replace it with the first key from the right sibling. If the jth child is not a leaf node, we also take its first child and append it to the children of the ith child. If it was the left sibling that had at least t keys, rather than the right one, the logic and code is symmetric to the case above, so we won't go through it line by line. Finally, we call delete on the ith child to continue the recursion, confident that it has at least t keys. Let's look at case 3a on this example B tree, which we duplicate for clarity. We'll assume that we are calling delete with key 5. The next node we would like to travel down to in our deletion search is the leftmost node corresponding to I equals 0. However, this node doesn't have t keys. Fortunately, its right sibling does, so our conditional evaluates to true. We get the index of the sibling with t keys, which here gives j equals 1. We check which sibling we are dealing with, which here is the one to the right. Our next step appends u's ith key to those of its ith child. Then, we transfer the 0th key from the right sibling up into u's ith key position. We check if the sibling was a leaf. Since it wasn't, we take its 0th child and add it to the children of the ith child. Now that the ith child has at least t keys, we can call delete recursively on it, and we are done with case 3a. The second subcase to be handled when we reach an internal node without a key is case 3b, where neither sibling of the ith child has t keys, so we perform a merge. Continuing our function from before, we first check if I is greater than 0. If it is, then we call merge children to merge the ith child with the left sibling, and decrement I by 1, since we now have one less child to the left. Otherwise, I is 0, so we merge with the right sibling. In either case, if u was the root and has become empty, we update the B tree root to point to u's only child, decreasing the tree height. Finally, we call delete recursively on the ith child. Let's see this in action on an example B tree, which we duplicate for clarity. we'll delete key 1. This will correspond to I equals 0. So we jump to the else statement and call merge children, which merges the 0th child and the first child of u. We check if u was the root in case we've made it empty, but it isn't. So we call delete recursively on the ith child, and we are done with this case. Before wrapping up, one helper function we haven't yet implemented is merge children. This function merges the ith and I plus 1th child of a node u when both children have t-1 keys. The merge is performed around a median key which is pushed down from u. The function takes a B-tree instance, a node u, and an index I representing the first of the siblings to be merged. It first takes the ith key from u to form the median of the merged node and appends it to the keys of its ith child. Then it takes the keys from its sibling and extends the ith child's keys with these two. Next, if the ith child is not a leaf, then we take the sibling's children also and concatenate them with the ith child's children. Finally, we drop the I plus 1th child. Let's see how this works in practice on a B-tree with minimum degree 2, which matches one we saw earlier, and which we duplicate for clarity. We call the function with u as the top node shown here, and with I equals 0. First, the ith key of u is popped, and then appended to the keys of its ith child. Then the keys of the I plus 1th child are copied over. We check if u is a leaf. It isn't. Since all leaves are at the same level in the B-tree, that means that its sibling is not a leaf either, so we copy the sibling's children over to the ith child. Finally, we drop the I plus 1th child, and we are done. When considering the complexity of our deletion procedure, note that when we make successor and predecessor calls, our function then terminates after a constant number of steps. So we can still think of our function as being one pass, even though we go further down the tree than the node where we delete the target key. Recalling that our tree height is big O log base T n for n keys, our CPU cost is the same as for search and insertion, involving a linear scan at each node and some constant number of additional operations, leading to a total cost of big O T log base T n. In terms of disk cost, we make a constant number of disk access calls to read and write blocks at each level in the tree. So the complexity is big O of log base T n. One extra point that's useful to be aware of is that in practice, the vast majority of keys are deleted from the leaves of a B-tree, since that's where most of them live, when T is set to a typically large value. Before closing, we'll briefly mention a couple of other B-tree variants that we did not discuss here. The first is the B plus tree, in which all values associated with keys are restricted to the leaves, and leaf nodes can be directly linked to make traversal across leaf nodes faster. The second is the B star tree, which aims to keep non-root nodes a bit more full, with minimum 2/3 occupancy rather than 1/2. As you'd expect, each of these choices comes with pros and cons that can make them better or worse suited to different scenarios, but their overall behavior is broadly similar to that of the standard B tree. In the video description, you can find links to Python code to implement B-trees, slides, and references. I hope you have a wonderful day.